how many of you understood the concept behind graph neural network? Okay, I will briefly go through the introduction again, and then we'll quickly go through the introduction and then move on to the to this blog further. So graph neural networks are used for uh, basically modeling the data sets on a graph. In a graph, you have nodes and you have the edges, or what we call as the links. We have these are the vertices, vertex, edges, and you have the global attribute. So mathematically, the nodes are represented as embeddings, and the links or the edges are also represented as embeddings in a graph. And you can have an undirected edge, so you can have like something like this, which doesn't have any arrow, and you can also have a directed edge. So you have a directed graph and undirected graph. We can also consider images as graphs. So each pixel in the image can be considered as a node. So for example, here 00, 10, 20, 30, 40. So each pixel here is a node in the graph, and you can represent the image graph in either as in this form, wherein you have the image uh, and you have the links. So, or you can represent it as the adjacency matrix. So in the adjacency matrix, you have on both the axis, you have all the nodes. So and a 1 in the adjacency matrix represents whether there is a link between the two nodes or not, and a 0 represents that there is no link between the nodes. Or you can represent it as kind of a graph. We can also have text as graph. So this is the example of sentence wherein you can consider each word to be a node in the graph, and this is a directed graph. So you can see we have these arrows, and so R is connected to graph and is connected to, so all is connected to R. So this is the way you have uh, you have the connections. The connections are only from a node to another node. So you have this connection from R to all, and but you don't have a connection from all to R. So you can see that this cell is empty, but this is one. So you can also have graph valued data in the wild. So for example, the molecules in chemistry, you can consider uh, each atom to be a node in the graph, and the bonds to be edges or links in the graph. So also social media networks or social networks form a very good example for understanding the graph data structures. So you can see that uh, these are these are the different users on the social network, uh, both on both the axis, and this is the adjacency matrix showing the linkages between or the connections between the different users, and this is the graph which represents just the nodes and the links. So the text data and the image data. So their adjacency matrices are like for text data it is diagonal, and you have this kind of a banded structure in an image data set. However, for an unstructured data like social networks, you can have some kind of complex this kind of complex looking adjacency matrix. Other examples are citation networks, or you have something known as knowledge graphs. So how Wikipedia links are connected to each other. Now, we discussed about the different types of problems that can be addressed by the graph structured data. One is a graph level task. So in a graph level task, you have to basically classify the entire graph. Uh, for example, the image graph, or this is the molecule. So you have to label it as some kind of a disease or no disease, or you can even think of like an image graph, and you want to classify it as cats or dogs. Then we have the node level task, and in node level tasks, you have to predict the or you have to find out the properties or attributes of the nodes. So, for example, so they say that a classic example is the Zach's Karate Club, and the dataset is a single social network graph made up of individuals that have shown allegiance to one of the karate clubs after a political drift. As the story goes, a feud between Mr. High and John X creates a schism in the karate club. The nodes represent individual karate practitioners, and the edges represent interaction between the members outside of the karate club. So you have basically two instructors. So one is you have an instructor, Mr. High, and then we have this another person, John A. Now they are having a fight, and they are basically making groups, and you have to basically predict the node level property. So the nodes are the different members of the karate club. A corresponds to the group which is having its allegiance to John, and the red corresponds to the members who have allegiance to Mr. High. So this is a kind of a classification example for uh, for a node level task, and then we have the edge level task. So in the edge level task, we have to basically predict the edges. So for example, one problem can be to understand image scene understanding. So what is going on in this image? So first, what we'll do is we would run this the uh, through an image segmentation algorithm. So you basically segment and find out the objects in this image, and so the objects are the nodes of the graph. And now, if you choose to discover the connection, so we can consider the graph as fully connected based on their predicted value prune edges to arrive at a sparse graph. So these are the edges that you have to predict. So you first of all create some kind of a label data set in which you pre-process your images through an image segmentation algorithm, which will identify the different objects for you. And for the different objects, then you label these links. Whatever links are truly present, have a training data and have a test data set. So in this case, you are given this image, and we want something like this. We want to know what all objects are present, what are they doing, and so yeah, this is where I think we ended last time. Now, coming to the challenges of using graphs in machine learning. So how do we go about solving these different graph tasks with neural networks? So the first step is to think about how we will represent graphs to be compatible with neural networks. So you have to think of merging the graph with neural networks. So how you would do that? So machine learning models typically take rectangular or grid-like arrays as input, so it's not immediately intuitive how to represent them in a format that is compatible with deep learning. Now, graphs have up to 4 types of information that we will potentially want to use to make predictions. So one is nodes, edges, global context, and connectivity. So these are the 4 different types of information that we want to make predictions on. And the first three are relatively straightforward. So for example, with nodes, we can form a node feature matrix n by assigning each node an index I and storing the feature for node I in n. So you have a feature matrix n, and each uh, index or each row in that feature matrix n represents a particular node. So I is the kind of an ID for that particular node. Now, while these matrices have a variable number of examples, they can be processed without any special technique. So it's relatively easier to just process this kind of node feature matrix. However, representing graph connectivity is more complicated. So perhaps the most obvious sizable. Now we saw the examples, we have seen the examples of using TensorFlow, and there is another library that I think most of you would be aware of, which is PyTorch. So in deep learning, all the data structures, that we use are basically tensors, and uh, so so they say that you can basically represent the connectivity in a graph as an adjacency matrix, but this has a few drawbacks. So I think we saw this last time that, okay, so if you have this kind of you can basically represent the same type of graph with different adjacency matrices by just changing the order of the nodes. So for this graph, this adjacency matrix is also valid. This adjacency matrix is also valid. So all these adjacency matrices are valid for the same type of graph. Now, one elegant way and elegant and memory efficient way of representing sparse matrices is as adjacency list. So rather than having the adjacency matrix, we would prefer the adjacency list, and these describe the connectivity of edge ek between the nodes ni and nj as a tuple I comma j in the kth entry of the adjacency list. So you have these two nodes ni and nj. These are represented as tuple I comma j, and this is the kth connection, or this is the kth entry of the adjacency list, and it is represented by the by the edge ek. So for example, this one, so this is the edge. Uh, these are the different uh, edges, and these are our nodes. These are our different nodes, and we have an adjacency list here, so which represents what are the different nodes which are connected to each other, like the ID of different nodes. And so since we expect the number of edges to be much lower than the number of entries in the adjacency matrix, so in the adjacency matrix, the number of entries in an adjacency matrix will be, so if you have 4 nodes, you will have 16 entries in the adjacency matrix. So basically, it's a the would be that would be required would be higher. It's a computationally expensive task, and we avoid computation and storage on the disconnected parts of the graph. Uh, so for the adjacency list, you would not have any entries, or you would not save the data for the cells in the adjacency matrix for which there is no link between the nodes. And now to make this notion more concrete, we can see how information in different graphs might be represented under this specification. So it can be noted that the figure uses scalar values per node or edge or global, but most practical tensor representations have vectors per graph attribute. So instead of a node tensor of size and nodes, we will be dealing with node tensors of size n nodes, comma node dimension. So we will basically embed the node tensor in an in some node dimensions, and so that's how it will be represented. And same for other graph attributes, that is the edges and as well as the entire graph. Now, graph neural network. So now that the graph description is a matrix format, that is permutation invariant. Now, what was permutation? So this kind of representation with a adjacency list is permutation invariant. So uh, you for this kind of an adjacency list, like you cannot have two different adjacency lists corresponding to the same graph, but we saw that for the same graph we saw the different adjacency matrices. So this is not permutation invariant, but this is permutation invariant. So if you do a permutation combination of, like if you even change the location, you have 20 as the first member, 10 as the second member of the adjacency list, but the graph that so it is the same adjacency list, and I cannot do something like make add a new element here. So to change this adjacency list, that's the thing that we have to do, add or subtract or do something. The graph will change. So we have a representation which is so this word is very important. So we say that this graph description is in a matrix format, that is permutation invariant, and we will describe using graph neural, which we will describe using graph neural network to solve graph prediction tasks. Now, graph neural network is optimizable transformation on all the attributes of the graph. So you have a transformation. So what is a transformation? It's like it's a function or it's a mapping. For example, we were trying to map or transform from the images to the classes. For example, the cats and the dogs example data set. So we were creating a mapping function which given the image, it can tell us what is the label or what is the class. So graph neural network is an optimizable transformation. So we do certain optimization, we reduce the loss, we have a loss function, we do gradient descent. Now this optimizable transformation happens on all the attributes of the graph, the nodes, the edges, and the global context, that preserves the graph symmetry. So it basically preserves the graph symmetry, that is it is so preserving the permutation invariance. uh, that's the task that we have been like, that's the goal that we have. So in that transformation, our the property of permutation invariance should not change. So the graph symmetry should not change. And we are going to build graph neural networks using the message passing neural network framework proposed by Gilmer et al. Using GraphNet architecture schematics introduced by Petaglia et al. So this is that paper, 2018, Relational Inductive Biases, Deep Learning and Graph Networks. So graph neural networks adopt a graph in, graph out architecture. So you basically have a graph as input and a graph as output. And so which means that the model accepts the graph as an input with information loaded into its nodes. So how is the information loaded into its nodes? You basically embed the nodes using the, so each node is not just a node now, it's a vector. You have an embedded representation of each node. So the information is loaded into its nodes, edges, and the global context, and progressively transform these embeddings without changing the connectivity of the input graph. So what we have to do is we have to transform the embeddings without changing the. So this connectivity should not change, but we have to transform the embeddings of the graph. So that's the task that uh, we have to perform while doing graph neural networks. And so the simplest graph neural network, now with the numerical representation of the graphs that we have constructed above with vectors instead of scalars. So we are now ready to build a GNN, and we'll start with the simplest GNN architecture, one where we learn new embeddings for all the graph attributes, that is nodes, edges, and global, but where we do not yet use the connectivity of the graph. So we have the nodes, the edges, and we have the global attributes, but we do not use the connectivity yet. And now this graph neural network uses separable multi-layer perceptron. Multi-layer perceptron is nothing but a simple scalar neural network on each component of the graph. So we call this a GNN layer. So for each node vector, we apply the MLP and get back a learned node vector. So you apply to each node vector a multi-layer perceptron, and you get in return you get another node vector. And we do the same for each edge, learning a per edge embedding, and also for global context vector, learning a single embedding for the entire graph. So you basically have three transformations that are going on: FUN, FVN, and FEN. So in this case, so what is V? V is our vertex, E is the edge, and U is the global. So for the so this is the vertex or the node, then this is the global. So you have one global transformation, you have one transformation for the vertices, and you have another transformation for the edges. So a graph is the input, and each component gets updated by MLP to produce a new graph. Now each function subscript indicates a separate function for a different graph attribute in the nth layer of a GNN model. Now, as is common with neural network modules or layers, we can stack these GNN layers together. Now, because a GNN does not update the connectivity of the input graph, we can describe the output graph of a GNN with the same adjacency list and the same number of feature vectors as the input graph. So this out that's the uh, graph data structure that as it exists. So we are not changing it. And on the other hand, for the output graph also, we will keep the same connectivity, same adjacency list. Now, but the output graph has updated embedding, so the embeddings are updated, and since the GNN has updated each of its node, edge, and global context representation. So these embeddings of the nodes, the edges, and for the global representation, those embeddings are updated, but the adjacency list of the output graph remains the same. Now, graph neural network predictions by pooling information. So we have built a simple GNN, but how do we make predictions in any of the tasks we described above? So we will consider the case of binary classification, but this framework can be easily extended to the multi-class or regression case. If the task is to make binary predictions on nodes and the graph already contains node information, the approach is straightforward. So for each node embedding, apply a linear classifier. So for example, you have this graph as an input and you want to perform the node embeddings. That is the you can see you have a binary classification task at hand, and you are basically trying to classify each node. You can see the different colors, the green and the red. However, this is not so always so simple. And for instance, you might have information in the graph stored in edges, so but no information in the node. But still, you need to make prediction on the node. So we need a way to collect information from the edges and give them to node for prediction. So we call this, we can do this by pooling. So what is pooling? Pooling proceeds in two steps. For each time item to be pulled, gather each of their embeddings. So for example, this item, this node, gather all the each of the embeddings uh, of the edges connecting this node, because in this case we do not have the information on the node. So you just take, so this is the embedding for this edge, and you just take these different embeddings, aggregate the information, and that is the embedding for this node. So similarly, you will gather the information or pool the information for this second node and all the different nodes. Now the gathered embeddings are then aggregated usually via sum operation. So you can use different operation. You can use max, min, sum. But they're saying that generally a sum operation is used. And we represent the pooling operation by the letter rho and denote that we are gathering information from edges to nodes as C, E to En to Vn. So from the edges, we are gathering information on the nodes. So if we only have edge level features, we are trying to predict the binary node information. We can use pooling to route or pass the information to where it needs to go. So you can basically pass the information from the edges to nodes. So you get the information on the nodes now, and then you can perform the binary classification on this on each node. So if we only have node level features and are trying to predict binary edge level information, the model looks something like this. So if you have only node level information, so you now it consider it to be the opposite case. Like you just have information or embedding for the node, and you want to basically perform edge prediction. So you will gather the information, you will then pool the information from the nodes to the edges, and then you will perform the task. So in this case, we are doing binary classification. If we only have node level features and need to predict a binary global property, we need to gather all the available node information together and aggregate them. So this is similar to global average pooling layers in the CNN, and this can be the same can be done for edges. So now in this case, if you want to predict some property for the entire graph, then you basically pool the information for all the nodes or all the edges, and you can do this kind of a global prediction. Now in our examples, the classification model C, so this is our classification model C, it can be easily replaced with any differentiable model or adapted to multi-class classification using a generalized linear model. So you can replace it our model C with any other different model, and this example is shown for binary classification, but you can also adapt it to multi-class classification, or you can even make it as a regression problem. So you have the input graph, you have then different GNN blocks. Now you have a transformed graph, and so this is an example of an end-to-end prediction task with a GNN model. And then on this transformed graph, you have a classification model, which basically does prediction for either at node, edge, or global level. Now we have demonstrated that we can build a simple GNN model and make binary predictions by routing information between different parts of the graph. This pooling technique will serve as a building block for constructing more sophisticated GNN models. If we have new graph attributes, we just have to define how to pass information from one attribute to the other. So now note that in this simplest GNN formulation, we are not using the connectivity of the graph at all in the GNN layer. So we are assuming that we are just keeping the connection as it is. We are not changing or using the connectivity of the graph at either of the GNN layers, and each node is processed independently as is each edge. So each node and each edge you basically process differently, but you will have a common function to do the transformation from the nodes to nodes, or edges to edges, or entire graph to entire graph. So that's what we saw, that you can have the three transformation functions. These three, you can have this kind of these three transformation functions. And we only use connectivity when pooling information for prediction. So when only the connectivity is only used when you are uh, pooling the information and passing messages between parts of the graph. So we could make more sophisticated predictions by using pooling within the GNN layer. So within the GNN layer also you can perform pooling. So what we mean by that is, so these are the different GNN layers, and in order to make our learned embeddings aware of graph connectivity, so you can, so if you use pooling within the GNN layer, your embeddings will learn the graph, will be aware of the graph connectivity, and we can do this using message passing. So message passing is a very common concept in HPC. It is used. NPI is the library, message passing interface. It's used across the different models, like the numerical weather prediction models, the any kind of parallel model that you will hear. So you can even they are giving this example of neural message passing for quantum chemistry. You can you can see examples from different fields where this message passing is used. So you can do this using message passing, where neighboring nodes or edges exchange information and influence each other's updated embedding. So message passing works in three steps. So for each node in the graph, gather all the neighboring node embeddings or messages. So what are the messages that a node will collect? Basically, it will collect all the neighboring node embeddings, and so which is the G function described above. So we have seen the G function, and now you aggregate all the messages via aggregating function. So for example, for this node, this is connected to this node, and this node. So this the filled node is connected to those three nodes. You basically the four nodes, not the three nodes. So you basically gather the embeddings for each of these nodes, like and the original node as well, and you aggregate the information. So you perform that kind of a pooling operation. So you can see this guy is just connected to two nodes. So that is the only place you are using the connectivity in the graph. So you gather the information, aggregate the messages via aggregating function like sum, and all the pooled messages are then passed through an update function, usually a learned neural network. So then you perform the transformation from layer n to layer n plus 1, and so in this layer, so you have the transformation function, and which will update the information. So it will update the graph information from layer n to layer n plus 1. So just as pooling can be applied to either nodes and or edges, message passing can occur between either nodes or edges. So these steps are key for leveraging the connectivity of graphs, and we will build more elaborative variants of message passing in GNN layers that yield GNN models of increasing expressiveness and power. So we have seen the this sequence, and so this sequence of operations, when applied once, is the simplest type of message passing GNN layer. Now this is reminiscent of standard convolution. In essence, message passing and convolution are operations to aggregate and process the information of an element's neighbors in order to update the element's values. So both are basically some kind of mathematical operations which are which are used to aggregate or process the information of the neighboring element. So even convolution, if you remember, you pass the filter, you run the you convolve the filter on the input image, and it will basically aggregate the information of the not just the center cell of the image on which it is being applied. It will gather the information of the neighboring cells as well. Now in graph, the element is a node, and in images, the element is a pixel. That's the difference. However, the number of neighboring nodes in a graph can be variable. So unlike in an image where each pixel has a set number of neighboring elements. So in a graph, it's not like just like images. It's like in an image, for example, uh, a pixel can only be connected to at max so 3, 3, 6, and 2, 8. So a pixel can be connected to at max 8 other pixels, but in a graph, a node can be connected to more or less number of nodes. And by stacking message passing GNN layers together, a node can eventually incorporate information from across the entire graph. So when you stack these different GNN layers together, this nodes of the graph, it can incorporate information from the across the entire graph, because pooling is happening. And what is pooling doing? It is aggregating information from the different nodes. So a node has information about the node 3 steps away from it, and we can update the architecture diagram to include this new source of information for the node. So this is the schematic for a graph convolution network architecture, which updates the node representation of a graph by pooling neighboring nodes at a distance of 1 degree. Now, learning edge representation. So our dataset does not always contain all types of information, that is nodes. So what are the different types of information in a graph? You can have node information, edge, or you can have a global context. So, but your dataset always cannot have all the types of information. Now, when we want to make a prediction on nodes, but our dataset only has edge information, so we showed above how to use pooling to route the information from edges to nodes, but only at the final prediction step of the model. So when you want to make the when you want to make a prediction on the nodes, but you have the information of the edges, that the embedding of the edges. So only in the final prediction step you will pool the information from the node edges to the nodes, and we can share information between nodes and edges within the GNN layer using message passing. So we can incorporate the information from neighboring edges in the same way we used neighboring node information earlier, by first pooling the edge information, transforming it with an update function, and then storing it. So just like we have seen here, we aggregate the information for the nodes. We aggregate the information from the neighboring nodes. We use a transformation function, and we update the embeddings or update the graph information for the nodes. You can do the same thing for the edges. So for the edges also, you can incorporate the information from the neighboring edges, and by performing pooling, you can transform it with an update function and then store it. However, the node and edge information stored in a graph are not necessarily the same size or shape, so it is not immediately clear how to combine them. One way is to learn a linear mapping from the space of edges to the space of nodes and vice versa. So how to basically pool or how to transform from the node space to the edge space, or from the edge space to the node space. So you will have to learn a linear mapping from the space of edges to the space of nodes. And alternatively, one may concatenate them together before an update function. So which graph attributes we update and in which order we update them is one design decision when constructing the GNN. So we could choose whether to update node embeddings before edge embeddings or the other way around. This is an open area of research with a variety of solutions. For example, we could update in a weave fashion. So there is this method uh, known as weave fashion, in which you can update the so whether you would want to update the nodes first, or you would want to update the edges first. So here, wherein we have 4 updated representations that get combined into new node and edge representation. So which are node to node, edge to edge, node to edge, and edge to node. So you can see. So first is this one is node and then edge learning. So you first learn the node and then followed by the edge learning. Now in this case, you first learn the edge and then you perform the node learning. Now this is weave layer. So in weave, you have both. So you have node to node. So you have node to node, and then you have edge to edge. So you have an edge to edge, and then you have basically have node to edge, and then you have edge to node. So this is a weave layer by which so this is a particular method or a design choice how you will update the graph attribute. Now adding global representation. So there is one flaw with the networks we have described so far. Nodes that are far away from each other in the graph may never be able to efficiently transfer information to one another. So if the nodes are far, even if we are performing pooling, the information it might not be possible that the information from one node to another node, which are far from each other in the graph data structure, they are exchanging information with each other. So even if we apply message passing several times, so for one node, if we have k layers, information will propagate at most k steps away. And this can be a problem for situations where the prediction task depends on nodes or group of nodes that are far apart. So one solution would be to have all nodes to be able to pass information to each other. So, and unfortunately for large graphs, this quickly becomes computationally expensive. And although this approach called virtual edges, it has been used for small graphs, but for big graphs, this becomes a problem. And one solution to this problem is by using global representation of the graph, which is U, which is sometimes called a master node. So this U representation, this is like a it's called a master node or a context vector. And this global context vector is connected to all the other nodes and edges in the network. So it is connected to all the nodes and edges and can act as a bridge between them to pass the information. So you can consider it or think of it to be like a superset and or some kind of a node or master node or a context network, which is context vector, which is connected to all the other edges and the node, and it can act as a bridge and it can pass information between the different nodes. So now even if two nodes are far away from each other in the graph, you can pass the information via the master node. So this creates a richer and more complex representation of the graph than could have otherwise been learned. So in this view, all graph attributes have learned representations, so we can leverage them during pooling by conditioning the information of our attribute of interest with respect to the rest. So for example, for one node, we can consider information from the neighboring nodes, connected edges, and the global information. So that's the uh, so you can leverage these three features. So all the neighboring nodes, so adjacent nodes embedding, adjacent edges embedding, and the you have one is the global embedding. Now to condition the new node embedding on all these possible sources of information, we can simply concatenate them. We can just concatenate all these three information, and additionally we may also map them to the same space via a linear map and add them or apply a feature-wise modulation layer. So which can be considered a type of feature-wise attention mechanism. Now we have the CNN playground, and okay, so there are some more basics which are left. So we can cover this in the next class, but I would like to bring machine learning conference. There is this graph neural network session which is happening, and there are these graph neural networks. They're having a session on graph neural network tutorials. Let me just see where they are. ICLR tutorials. So rather than just having the conference as basically computer. So rather than just having the conference, they are also having these tutorial sessions. Yeah. So yeah. Now ITLR 2022, it will happen in some time, and you can go and see the different graph GNN tutorials that are so when you are doing deep learning with graph, it's also known as geometric deep learning. So they are ICLR had this graph neural network tutorials. So you can go and check Signet Kibru stock, or like there are different people who are working in this area, and these are like still a lot of work is happening in the. So one of these graph neural network tutorial that was accepted is this one. So this is a book uh, which is which is published, and so they have prepared this graph neural network tutorial, and there is a so they will present this in the graph tutorial session in ICLR, and there are even graph attention network. So you can search. It is like combining the transformers and the graph neural network. So recently I saw one paper on graph attention networks. But anyways, so this is a very active area of research, and